All right, welcome to Tuesday's lecture. There's not a whole lot of administrative announcements today. The first of which I want to say that as per last night's announcement, I have given all the tutorial sections, or I should say practical sections, a one-day extension for the lab. This should allow everybody to take their marking feedback from lab 1 and give you some extra time to sort of take any feedback the TAs had. And then that way you can implement it and submit it in time for lab 2. So this is like a one-time extension. It's not because people were busy or anything. It was just because it just seemed fair to see your marking feedback before you you have to submit your second lab. And the second administrative announcement is there was a survey posted last night. The link is in the announcement, so you can go find the survey through the announcement. And it's a vote on a one-time exception on a policy that's listed in the syllabus. So because it is listed in the syllabus, we do have to have a majority vote in the class to do something differently. So I believe the vote closes tomorrow at 11 a.m. So it's just over 24 hours of voting time. So you can have a read through the survey there, and it should tell you all the information if you'd like. Okay, I don't think there's anything else to discuss in terms of administrative tasks. I think we should just kind of get on with the lecture now. So let me screen share. Okay, so today, there we go. Today we are done with energy. We did some review problems yesterday with energy. Hopefully I dogged you from last Wednesday's lecture when we concluded energy. And hopefully you had some time yesterday, a bit of a breather between the midterm and everything, and you had some time to do some energy homework problems. Today we're going to move on to momentum. And as you've noticed in this class, I do try to tell a story about kind of what we're doing and why we're doing it. And there's definitely a logic behind why one thing before another thing, and why we don't teach some things at all. So I've been trying hard to make sure the puzzle in your head has all the puzzle pieces for you to sort of see the big picture and not just see every chapter individually as a separate puzzle piece. So we're going to do the same thing with momentum. It does absolutely fit into the story. You just have to be told what the story is. So the big picture so far, up until the end of energy, is our talks so far have been pretty much categorized into two big umbrella categories. The first umbrella category was mechanics. And as the name implies, mechanics kind of means like machines or motion. And under the mechanics category, we studied both dynamics and kinematics. And dynamics was forces with Newton's laws, and that's what causes motion. And then assuming something is already moving, we studied kinematics, which means, once it's already moving, where's it going to go? Like trajectory analysis. And those two kind of blend together very naturally, right? One flows, hence the arrow, dynamics, arrow, kinematics, right? One flows into the other one. Then we kind of moved into energy, and energy was different. We didn't really draw free body diagrams. I know there were a few questions that needed piggybacking on dynamics, but for the most part, energy is self-contained. The notion of energy is an integral of force over a distance, and it's pretty much self-contained. Why did we need energy? It was because dynamics moving into kinematics did not satisfy our analysis needs, right? The dynamics kinematics blend only handled constant acceleration systems. And there's a lot of things that do not have constant accelerations, primarily things that do not have a constant force. So we looked at Hooke's law, for instance, does not have a constant force. Newton's law of gravity, gm1 and 2 over r squared, does not have a constant force. Most vertical circular motions, for the most part, don't have a constant velocity. And if they don't have a constant velocity, they don't have a constant acceleration, which means they don't have a constant net force. There are scenarios in which vertical circular loops do have constant velocity, but they're rare. They are very rare in real life. So most vertical loops, in fact, do have a variable speed as you go around, you know, because now that we know energy, mg delta h, right, at the as your kinetic energy takes you up and around, you convert some of that kinetic energy into gravitational potential energy, thus reducing your kinetic energy. So you are transforming your speed as you go around. So there are three main categories in this class alone, and this is a very idealized class, right? It's only first year physics. So there's three main categories that you'll see in this class that have variable forces. So that's where energy came in. It was a band-aid sort of for getting over the hump of a variable force. So really, what is there left to study? It looks as though we've looked at things that cause motion. We've looked at the trajectory at which motion exists. We've looked at the band-aid fix for when we have a variable force. So, you know, what is there left to do? Let me depict for you a thought experiment to motivate kind of where we're going with this. So, this is an obvious answer. Would you prefer to get shot? Which is hopefully the answer is no. It doesn't even matter what the alternative is. Hopefully the answer to that is no. Do you prefer to get shot or play catch with a bullet? And it's a bit of an extreme example, I know. So before you get all eyes wide and wondering where I'm going with this, it's a little bit extreme, but hopefully playing catch with a bullet is far more appealing. You know, you're just kind of tossing an object back and forth, you know, kind of like pitching a baseball back and forth. And if you were, you know, being shot at, you would run or move, obviously, right? However, the point of this extreme example is that it's the same object in both cases, right? It's a 10-gram bullet in both cases. One is being fired at you quite fast, and one is just being lobbed at you. So it's the same mass, but just different speed. And you know, your brain has an innate ability to understand what is bad and what is dangerous. And a light mass traveling very quickly is still, your brain tells you, is a very dangerous thing. So you move your bum out of the way. I could kind of flip that. For those of you who are familiar with UTM, you might know this. We have this giant obelisk statue at the opening of our main entrance near the Davis building. And this giant obelisk stone statue was, I think, just over $1 million, probably like $1.3, $1.4 million to build. And I mean, it looks nice. It's just a giant pile of rocks at the end of the day. So I don't see why they felt the need to spend all that money when they're hiking tuition every year by 10%, which is ridiculous. Anyway, so they spent a bunch of money on these rocks, and it looks like a giant pile of rocks. What if, hypothetically speaking, a part of this giant obelisk statue at the front of UTM were to break off and fall from, I don't know, maybe about 20 feet in the air? It's not that high. It's, you know, maybe about 20 feet, I'd say. Well, if that falling rock was to fall from rest at 20 feet in the air, it is traveling substantially slower than this bullet, for instance, you know, this bullet being fired out of the gun. So the velocity of this chunk of rock falling from 20 feet is far slower. Like we're talking like, you know, half a meter a second versus a bullet that gets fired at like 400 meters a second, like very different orders of magnitude. However, your brain wouldn't sit here thinking, oh, hey, look, this rock is above me, but it's okay. It's only traveling half a meter a second. I don't need to move. So that kind of tells you that, you know, size isn't really everything. You know, a very light bullet, 10 grams, traveling super fast, will definitely make you hustle away. But also, you know, a small rock, well, not a small rock, like a medium-sized rock falling at a very slow speed will still make your bum move out of the way. And your brain knows this. I don't have to teach you physics for your brain to know when to get out of the way of a moving object and when not to. You know, I could give you endless examples like this. I mean, if you have a car that you park on the driveway and say you forget to put the parking brake on, I don't know. and you start to see your car slowly starting to kind of inch backwards. Someone who is stronger, they might get behind their car and push on the trunk to stop the car from moving. For the most part, that's decently safe. I do not advise getting behind a moving vehicle, of course, but I've driven a standard and I've done that myself. I forgot to put the parking brake on the car, and I get out of my car, I start to see it move. So it's not hard to go stand behind your car and just kind of lean against it to stop it from moving. Even though my car is really, 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 really heavy, your brain sort of gets a sense of, okay, well, even though it's heavy, it's really not moving that fast. So it's kind of safe for me to put your body in front of it and stop it. So your brain has this innate ability to sort of factor in size and speed and tell your adrenaline system to either kick in and run or chill out and not care. So that's really what we're getting at here with momentum. And more specifically, we in terms of physics, the piece of the puzzle that's missing is we've talked about what causes motion, dynamics. Assuming motion exists, we've talked about where it's going to go, right? Kinematics. We have talked about a band-aid for fixing the analysis of motion, which was energy. But we've very, very, very cleverly hidden from students up until now, we've never really talked about motion itself, right? We've said what causes motion, dynamics. Where's it going to go, kinematics. But what is motion? How much motion does something have? And this is what your brain does naturally. A fast moving bullet, even though the bullet is light, a fast moving bullet, your brain tells you this thing has a lot of motion, get out of the way. A slow moving rock falling from 20 feet, your brain says this thing has a lot of motion, get out of the way. So your brain knows it. It's more than just speed, and it's more than just mass. And this is where momentum comes in. It's speed times mass. That's momentum. And that's how we quantify how much motion something has. So here is the definition of momentum, mathematically that is. And here I will say, note that momentum, also, for some reason, the variable for momentum is P. I don't know, for that silent P in momentum. I don't know. Clearly, it's based off of Latin. I'm being a little bit facetious. It's definitely based off of Latin. And it's a little bit presumptuous to assume that variables in a certain field should be labeled according to the English pronunciation of them. But still, it's funny to make fun of the fact that momentum has a silent P. Momentum is a vector. So if we look at the math for a second, you'll know that you'll see that the formula is mass times velocity. Well, mass is a scalar, but velocity, however, is a vector. So in terms of the math, this isn't a problem. We don't have to do a cross product. We don't have to do a dot product. All you're doing is you're taking the vector v, and you're scaling it by the scalar quantity m. So, if you're trying to do vector analysis, think back to grade 12 calculus and vectors for a second. You've got some sort of vector in space v, that's the blue thing, and you multiply it by scalar m, and this either makes it larger or smaller, but it does not change the direction. Okay, so this is what the vector nature of momentum is. So I will stress this because it is hugely important. Momentum is 100% a vector. Okay, now that we know the definition of momentum, let's just do a very, 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 very simple question here, just to illustrate kind of the math and also the vector nature. So what is the momentum of a 1,000-kilogram car moving? That's probably about a Civic, or I would say. Anything bigger than a Civic is probably more than 1,000 kilograms. What is the momentum of a 1,000-kilogram car moving at 15 meters per second? So let me change to black here. So the momentum is going to be mass times velocity, which means we're going to get a 1,000-kilogram car moving at 15 meters per second east And I mean, that's pretty simple, 1.5 times 10 to the 4. And then if you look at the units, you're doing mass, which is kilograms, and you multiply it by velocity, which is meters per second. So the units for momentum is just kilograms, meters per second. And of course, it's a vector, so we have to label it east. Now, you might be thinking newtons was mass times acceleration. So, you know, why didn't we just say, oh, a force had units of kilogram meter per second squared? We could have. We just chose to combine a kilogram meter per second squared into a unit called Newton. Why didn't we do this for momentum? Anyone's guess. If you can think of a good justification for it and you want to name the unit and you can convince the scientific community to do so, you can have a unit named after yourself. But there hasn't been such a case made. So the unit for momentum is simply just kilogram meter per second, and that's just supposed to be momentum. So I will underline this and say this is how much motion, this object has. Okay, sorry for my messy handwriting. I've got messy handwriting on paper. It's even worse on a frictionless tablet, or almost frictionless. I'm assuming it's frictionless. Haha, funny physics joke. Anyway, so yeah, so that's what momentum is. Momentum quantifies how much motion an object has. It's really how you compare apples to apples. It's how you compare a slow-moving heavy object to a fast-moving light object. You know, you look at the momentum. You look at how much motion that object has. Okay, now I hate to be a little bit of a hypocrite. I've been doing it less this semester. I often tell my physics kids that chemists lie to you. You know, in grade 11, they teach you the octet rule. Grade 12, they teach you the octet rule's wrong. They teach you other things. And then in first year, Judith Poe teaches you simultaneous equations, not ice tables, you know, and Vesper. And then in second year, you learn Vesper's kind of wrong. So, you know, I often say chemists lie to you all the time. And biologists, you know, they just tell you to memorize a bunch of stuff. There's more to it than that, of course. I'm obviously downplaying that significantly. But, you know, I often do try to say that physicists, we don't lie to you. What you learn in grade 11 is still applicable in first year and second year and third year and fourth year. However, I did lie to you a little bit, just ever so slightly, when I told you what F net equals ma was, or when I told you what Newton's second law was. So interestingly enough, dynamics was the idea of, you know, quantifying what causes motion, right? And momentum is the thing that quantifies how much motion something has. So it's natural to sort of wonder, why is F net equal ma not a function of momentum? Because, you know, you would think it really should be. You know, F net equals ma is the thing that explains what causes motion. And if motion is quantified by momentum, you would think the thing that causes motion should have motion in it as a variable. And if you have that sort of intuition or that sort of train of thought, I would congratulate you for one, because it's a very abstract idea. And I would also say you're absolutely correct. So before we go any further, I kind of want to show you what the real Newton's second law is. This is how Newton published it many, many years ago, back in the 1600s. And I will show you kind of where F net equals ma comes from and why we use it so prevalently without any qualifications. So first of all, let me just write this. Newton, oh, maybe not in red. Let me switch to black. Newton published his work as saying that the net force was in fact given by the derivative of the momentum of a particle. And at least to me, someone who intimately loves and knows physics, this makes more sense to me than m times a. But I 100% see where ma comes from. And you'll see very, very shortly. It's very simple, very simple. Before I get into the math, I will kind of point out the fact that there is a derivative on the page. And before everyone starts freaking out about calculus again, I know I've been bringing up calculus quite a bit in this class for it not being a calculus-based physics course, but I'm sure you've seen from the midterm, I am not testing you on calculus. I'm just kind of showing you these ideas in lecture, hopefully because this kind of provides you with a better background of the physics and kind of the interesting nature of how everything relates together. Anyway, it's also very simple derivatives. It's technically derivatives you've seen in grade 12 advanced functions. The only thing we're going to learn, perform here is product rule. Anyway, so given this definition of momentum, the definition of the net force is the derivative of momentum, we can actually go ahead and simply just swap that in. So we know momentum is given by mv. So it's the derivative of mv. And here, for those of you who are thinking of derivatives, you might already be there. You might be very tempted, I'm going to switch to blue just momentarily. You might be very tempted to say, okay, well, the mass of the particle is constant, so you can pull mass out, and then you get the derivative of v with respect to time. And the derivative of v, we know from kinematics, is just the acceleration. And there's where ma comes from. And 99.9% of the time, the mass of the particle as forces act on it is constant. And I mean, I can't even stress how true that usually is, 99.9. Like, you push a rock, it's got the same mass before you started pushing as it does after you started pushing, right? Most, like 99% of the things will retain their mass moving forward, as you push or pull them, right? However, generally speaking, science doesn't, there's no rule in science that says it has to have the same mass as you're pushing or as the object is moving. So if you assume that the mass is not constant with respect to time, then you cannot pull mass out of the derivative. And then you have to just simply perform product rule. So if you perform product rule, you're going to get the derivative of the first times the second plus the first times the derivative of the second. And as I said before, 99% of the time, the derivative of mass with respect to time is 0, most of the time. However, if that's not true, then your actual net force on the object is actually going to be the derivative of mass times the velocity plus the mass times the acceleration. And this opens up a whole new can of worms, because previously, when we were talking about energy, we were saying, well, if the acceleration wasn't constant, then the net force wasn't constant. And vice versa. We said if the net force wasn't constant, the acceleration isn't constant, right? Because prior to energy, a crucial thing was that the acceleration had to be constant. However, this true, beautiful form of Newton's law is actually a little bit more convoluted than you might think. Because here you see that the net force is a function of both speed and acceleration. And if you think about it, if there is an acceleration, then the object, let's say a second later, the object will be going slightly faster. So even if the acceleration is constant, hypothetically speaking, then a moment later, the velocity will go up, up, and up. Every second that goes by, the velocity will be getting faster, faster, and faster. And according to this generic form of F net, the faster the velocity, or the larger the velocity, the larger the net force. So even if you do have a constant acceleration, if mass is changing, this is a problem, because then the net force isn't constant, and then you can't use dynamics or kinematics anymore. So this is really, really, really why energy becomes very important, because there are some unique, very, very niche cases when you do have a constant acceleration, but the net force isn't constant, and then you need to piggyback on energy even then. Normally in class, when I present this, I ask students, if they have any ideas of when mass may not be constant. So I'm going to try that. I'm going to open the chat for a second. Does anyone have any ideas of when a particle may not have a constant mass with respect to time, and when we, more specifically, when would we need to use this true Newton's second law equation? So if you have any ideas, you can open your chat and try to guess. Too much friction causes part of a rock to break apart a little bit. Yeah, that's, I suppose, although it's hard to quantify that. If friction is a thing breaking pieces of rock off, it would be hard to turn that into a function, but I guess conceptually that's kind of true. When a bullet gets lodged in something, well, if a bullet gets lodged in something, okay, you're saying like the bullet exits the gun and strikes a piece of wood. Perhaps. I like Brandon's hint. I would continue on Brandon's train of thought. Radioactive half-lives, sort of. That wasn't quite where Brandon was going, I don't think. Okay, now we're getting somewhere. Particle enters a vacuum, not quite. Particle accelerators, we're getting somewhere. Why is particle accelerators kind of on the right track? Changing temperature causes something to change states and then mass. Not quite. Yeah, Brandon's right, warmish. Not quite, but close. Let's go back to particle accelerators for a second. Why might particle accelerators be kind of up there with why we need this? What about particle accelerators means we're changing the mass of something? No guesses yet. Yeah, again. Okay, it's okay. You guys are, some of you may never have taken physics before, so you may not have been exposed to these ideas in high school. Particle collisions, no, we're getting farther away. Does it have something to do with reaching the speed of light? Miriam, yes. Yes, it does. Good one. So that's one of them. I'm going to close the chat now, so if you say anything further, I won't see it. So based on what Miriam was saying, we learned, if you happen to take high school physics, which I'm not assuming you have, because that's not a prerequisite. Oh, now OneNote is frozen. Of course it is. Well, I'll chat until one. Oh, where'd we go? Never buy a Windows machine. Okay. Let's get this bigger again. Okay, if you've taken high school physics, then you might remember right at the end of high school physics, right at the end of the semester, you will have studied a unit called modern physics. So I'm going to say examples of when you'll need this. Okay. In modern physics, in grade 12, you learn about the theory, the special relativity. I mean, Einstein pioneered the field of relativity. By no means do you learn general relativity in high school, but you do learn the theory of special relativity in high school. And you learn that there's sort of a relativistic effect on various things. And you have this sort of factor of the square root of 1 minus v squared over c squared. And this gamma factor is actually multiplied by all of the dynamic and mechanic variables. So things like mass, for instance, you can say that the relativistic mass is going to be the initial mass divided by gamma. And this means that, now let me preface this by saying even this equation is not quite true. So before, if anyone sees this on YouTube later who is an actual physicist, please don't shoot me. I know it's not quite true. In high school, this is how they choose to teach relativistic mass. They say the equation predicts that when the speed approaches the speed of light, c, then you are pretty much doing 1 minus 1, and 1 minus 1 is 0. So near the speed of light, the relativistic mass approaches the rest mass divided by 0, which means that it approaches infinity. So if the particle is speeding up, now if the speed is like what cars travel at or planes travel at, we're nowhere close to the speed of light. So we don't really consider this equation. But in particle accelerators, when your whole job is to take a really, really small subatomic particle, like an electron or a proton, and then accelerate them super, 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 super fast, yes, your speed v is actually pretty close to the speed of light, like 0.8, 0.9 the speed of light, 90% the speed of light. And then you have to take into account this relativistic mass. And then as it's accelerating, it's continuing to speed up, which means the mass is changing. So the answer when you will need this for 1 is when you do relativity. So when you're doing any sort of relativity physics, you will need the real equation for Newton's second law. And the second one, there is actually a second common situation when you need this. And it's actually nothing complicated. It's not like particle physics or modern physics or anything. And I'll give you a hint. It has something to do with what Marc Garneau came in to talk to my students about a few years ago. That was kind of discussed on the test. He was talking about space physics. And okay, I guess I'll just spell out the answer because it's kind of hard to lead you there. When you have a giant rocket ship, most of the weight of that rocket ship is fuel. And when the rocket is like taking off, it burns fuel at an incredible rate. There's actually a hint there. I gave you a hint in the picture. You know, will the real Newton's law please stand up? I gave you a hint of a rocket ship taking off. So look at how small that rocket ship looks in the picture compared to the flame coming out of it. Clearly, the evidence of the scale of that flame tells you that it is burning mass at an incredible rate. And you know, as the rocket is taking off, it's designed to use up all of the launch fuel by the time it hits the upper atmosphere. You know, when it kind of escapes the majority of Earth's atmosphere. So it probably takes maybe about 10-15 minutes to get up and out of the atmosphere. So if that, maybe even shorter. So it uses an incredible amount of mass in about 10 minutes. So you can't necessarily ignore the derivative of mass with respect to time. I mean, you can even see there's kind of two parts to this picture. There's the actual rocket ship, that little white thing, and then there's a little silo thing on the other side. That silo thing is the gas tank, and the gas tank is oddly bigger than the rocket ship. So you have to use up an incredible amount of mass in a very short amount of time. So I would say the answer for number 2 or scenario 2, when do you need to use the real Newton's second law? I would say rocket physics. Or technically speaking, anything that burns fuel, technically as it drives, it will lose mass. So even your car, now the rate at which your car burns gas is substantially way smaller than the rate at which a rocket ship burns gas. So we kind of ignore that when we studied the physics of the car. And plus the weight of the gas tank is inconsequential compared to the weight of the car itself. So when you drive cars, we assume the derivative of mass is 0. So anyway, so those are the two situations in which if you're an actual physicist, you would, doing like modern physics with relativity or particle physics, or if you were like a space physicist like Marc Garneau was, then you would actually have to use the real Newton's second law. But both of which involve calculus, and this is not a calculus-based physics course, so we won't have to do that. But it's cool to think about. Okay, because this isn't a calculus-based physics course, we can make some fun approximations. So we know that the real Newton's second law is the net force equals the derivative of momentum with respect to time. But we don't deal with derivatives in this class, so we're going to do what every good physicist does, and we're going to fudge the math. This is exactly why mathematicians don't like us. So we can actually approximate the derivative by using a delta. We do this, actually you did this in advanced functions, grade 12 advanced functions. Grade 12 advanced functions teachers, they did a really good job at discussing limits and derivatives without ever mentioning the word limits or derivatives. You know, do you remember in advanced functions, you did IROC, the instantaneous rate of change, but you didn't call it a derivative. You didn't call it a limit. You know, you just, they told you to take, 1.001 and then 0.999 and you subtracted the two. Yeah, that's what we're doing. You can approximate the derivative, the instantaneous rate of change, with a delta. And you can actually rearrange this. You can rearrange this for the, and this is equation 4.1 in the typed notes. You can rearrange for delta P, and you can say that the change in momentum of a particle is given by the average force that's applied to the particle multiplied by the time at which it was applied. So if you push with 10 newtons for 1 second, obviously the object won't speed up very much. But if you push with 10 newtons for 5 minutes, its final momentum will be much larger than if you only pushed it for like a couple seconds, right? So physicists have called delta P the change in momentum. We've called it something special. We've called it the impulse. And in the English language, you know what impulse, if you look in the Oxford Dictionary, you can look up the definition of the English word impulse. And that's why we named this quantity impulse, because it fits the English definition of impulse quite well. Delta P represents kind of how much motion something receives from a push, right? A push meaning force F, and how much motion something receives meaning where did it end up compared to where it started, right? Momentum 2 minus momentum 1, delta P, delta momentum. And so in the event we need it in a question or something, I always use the term delta P because it's very concrete. You see the term delta P, it tells you P2 minus P1, right? It tells you right there in the symbol delta. We all know what delta means. For some strange reason, some books, not all books, some books have actually denoted a new symbol for momentum, J vector. Again, for that silent J in impulse. I honestly, we were doing so good with symbolic naming up until now. Mass M, acceleration A, velocity V, force F, tension T, force of gravity Fg, and then we hit momentum, and bam, everything just gets screwed up with the logic and conventional naming. I don't know why. Honestly, if I was the one in charge of naming these things, I would be long since retired by now. I would be such a prolific physicist that if I got to name the symbol for impulse, I would be retired. So clearly, I'm not the one responsible for naming these. I'm just going with what the scientific community uses. So I'm just presenting you the language is all. Anyway, I don't think there's actually a need for momentum in many of the physics problems. Sorry, not momentum, impulse, a huge need for momentum. There's not a huge need for impulse in a lot of the physics problems, but if you are doing practice in your textbook or something like that and you come across the terminology impulse or the symbol J, or they're asking you for delta P, I don't want you to be left high and dry. So at least now you have a little bit of context as to what impulse is. Okay, let's, we've done enough talking. Let's just kind of shut up now and do some questions. Let's get our hands down and dirty. So what velocity will a 40-kilogram child sitting on a 40-kilogram wagon, oh my God, that's a heavy wagon, acquire if pushed from rest by a force of 75 newtons for 2 seconds? A lot of words. Physicists don't like words, so let's just go down and kind of write some write the numbers. So a velocity, So 40 kilogram child, 40 kilogram wagon. So I'll say the total mass that we are dealing with here is 80 kilograms. What velocity? Okay, so they want to know what final velocity. What else did they give us? From rest. From rest means the initial velocity is 0, with a force of 75 newtons for a time duration of 2 seconds. Okay, so I think I've transformed all the words. In fact, if you list your unknowns, it's almost as long as the sentence itself, which is kind of hilarious. Okay, so we're asked for V final. Now, on a test or something like that, you would have to know enough physics on your own to kind of know what equation to jump to and what chapter to jump to. Because we just presented momentum and impulse, I think you can probably figure out we need to use impulse. But if you didn't know that and it wasn't, contextually appropriate, how might you figure that out on your own? Well, we can ask ourselves, okay, you were given mass, we're given force, and we're given delta T. If you wanted to, you could probably solve this using dynamics and then kinematics, right? Because we have a constant force F, the mass is constant, which means we don't use anything special with the real Newton second law, just simply F net equals ma. So if you wanted to, I'll solve this 2 ways. If you wanted to, we could do the first way, the long way. We could use dynamics first, and then we could use kinematics. So we could say the force F equals mass total times acceleration. So the acceleration of the object is going to be F over mass total. And then we now have acceleration. We have V final, V initial, and time. So we can use V2 equals V1 plus AT, and we're looking for V2. So this is going to be, V1 is 0. So this is going to be AT, which is F over mass total times time equals V2. So this was a mix between dynamics and then moving on to kinematics. That's a terrible kinematics, but you get the idea. So doing it that way, the formula we get is V2, V final, equals force over mass times time. Now, if we used concepts of momentum and impulse, we could say that the change in momentum is going to be force times time, right? That's the exact equation here. Impulse equals force times time. So we know what the force is. We know, well, the time is given as 2 seconds. And the change in momentum, well, the change in momentum is going to be momentum 2 minus momentum 1. And we're told, well, we also know what momentum is. Mass total V final minus mass total V initial equals Ft. Oh, that looks like a plus sign. Ft. And we're told that this thing is initially not moving. So then that gets us mass total V final equals Ft, which means my final velocity is going to be F over mass total times time, which is the same formula we got beforehand. So there's kind of 2 ways. I should label this as method 2. So there's kind of 2 ways to skin a cat. I don't know where that saying comes from. It's a little bit morbid. I'm definitely a cat person myself. But anyway, there's more than one way to skin a cat. So this is showing you kind of how you could do it the old way and how you could do it the new way if you wanted to. Next example. What average force will stop a 1,000 kilogram car in 1.5 seconds if the car is known to be moving at 22 meters per second? So this is a good sort of sanity check. For those of you who do drive vehicles, your car probably weighs about 1,000 kilograms. Actually, it's probably more. 1,000 kilograms is a light car. But anyway, on the low end, right? And if you have to stop the car in 1.5 seconds, that's 1 Mississippi, right? That's 1.5 seconds. It's quite a short amount of time. So pretty much this question is saying, think about if you were driving your car at 22 meters a second, and if you think about 22 meters a second, what is that in kilometers per hour? Well, 22 meters per second. How do you convert between meters per second and kilometers per hour? I don't know if you remember. Well, if you forget, you could always just do it systematically. So you want meters on the bottom, kilometers on the top. So 1 kilometer over 1,000 meters. And then you can say 3,600, nope, sorry. We're gonna want minutes, no, seconds on top, and hours on the bottom. So 3,600 seconds per 1 hour. So you actually multiply, oops, you actually multiply by 3.6, if you remember that from the first lecture. So 22 times 3.6, which is around 4. This is going to be around 88 kilometers per hour. So this is like around, I don't know, not necessarily a highway like the 401, but maybe like a major city street like here, Ontario, or Britannia, or something like that. So it's not a slow speed, I guess is what I'm getting at. So picture driving just under highway speeds, and you have to bring your car to a complete stop in 1.5 seconds, which is not a long time. How much force is required to bring the mass of your car to rest when you are traveling at such a fast speed? So we can use, again, we can use dynamics and kinematics. I think that takes longer, honestly. You can say that a change in momentum is going to equal force times time. And this says that the change in momentum is going to be momentum 2 minus momentum 1 equals force times delta t. And momentum 2 is desired to be 0, right? You're bringing the car to rest, minus mass of the car, oops, that looks like an O, mass of the car times velocity initially equals ft. And what average force? So force equals mass of the car, velocity of the car over time. So there's your equation, and you plug in all your numbers. You're going to get 1,000 times speed. What was the speed in meters per second? 22, all over 1.5. So you plug everything in. You can, if you wanted to, you can approximate it. Oh, I forgot a negative sign, sorry. Yeah, there should be a negative sign there. So that tells you the answer is negative, which means the force has to be backwards. That kind of makes sense. It's got to slow the car down. If you do everything here, you're going to get 1.5 times 10 to the 4 newtons. That's a large amount of force. That is about 15 kilonewtons of force. That is crazy. That is a lot of force. This is the physics behind operating a vehicle. And I am of the firm belief that if anyone is driving a car, they should have at least had experience taking a first-year physics class, because it's dangerous driving a car. It really is. You're driving a self-perpetuating chunk of metal. You know, a 1 or 2 ton piece of self-perpetuating metal. It's literally a weapon. So yes, I know you need a license and there's some sort of government kind of regulations about it, but I mean, nowhere in that process do people learn the physics of driving a car. And I think it's really important to know that, you know, if you are going 88 in a 50 zone and a child steps in front of you, the amount of force needed to stop that car, the force of friction is not able to provide. It just isn't. So in fact, that's actually an interesting side question. Let's take a second and look. Oh, I need to insert some space. We know how much force is required to stop the car from moving. How much force can it provide? So I can say how much force can the force of friction provide? Is it even 15 kilonewtons? I hope it is, for the sake of the safety of everyone around everyone around you when you're driving the car. We know the free body diagram of a car is going to be the force of friction slowing it down. and there's gravity, obviously, and the normal force. So we can say that the force of friction is going to be mu Fn, which is going to be mu mg. And we know this car is about 1,000 kilograms, and G is about, well, G is around 10. So mu times 10,000 newtons. Well, the force of friction, for one, let's assume mu is 1, okay, which it's not. Let's assume mu is 1. Even if mu was 1, at most, oops, that's an N. At most, let's say mu is equal to 1, then the force of friction would be 10 kilonewtons, which is less than the required 15 kilonewtons. And that's at best. At best, you're still 5,000 kilonewtons short of the required force to stop your car. So this tells you, this is hardcore physics that tells you if you are traveling 22 meters a second, it is likely impossible for you to stop your car in 1.5 seconds. You would need something other than friction to help stop your car. For instance, you could hit a post. You know, if you see a kid, you know you don't have the amount of friction to stop your car. So if you need to stop, you can swerve and hit a lamppost. You know, a lamppost stops your car by a contact force, right, by a normal force. And normal forces can provide up to whatever force they are able to before they themselves break. So, you know, it's not impossible to stop the car in that amount of time. It's just impossible to stop that car with friction in that amount of time. So just while you're driving, if nothing else in this class, hopefully it changes your driving habits. I don't know. When I drive, I am known to speed, but the caveat is I actually know physics. So I know exactly kind of what I need to do to maneuver and stuff like that. So I don't know. I'm a firm believer that everyone should be taking a physics class if they're behind the wheel of a 2-ton piece of self-perpetuating metal. Anyway, moving on. If you're anything like me, you can't even wash your car without thinking of physics of various aspects. Yeah, I've mentioned this. You know, this is kind of how half the midterm questions came to exist. I literally do my laundry and just stare at it and think of the physics. So, you know, there's that. So anyway, here's an example of me washing my car thinking of physics. Again, true story. You're washing your car with a hose that expels water at a velocity of 20 meters per second. At a rate of 1.5 kilograms per second. What is the force acting on the car? So this one is interesting. They're telling you that the derivative of mass with respect to time is 1.5 kilograms per second. Now, this isn't quite rocket physics, you know, it's not like we're using up that mass. This is just telling you how much mass of water is flowing out of the hose. It's like a flow rate. Think of like fluids. It's a flow rate. Now, where do you use this piece of information? This is where things get, it's honestly not that bad. It's just different. And I've mentioned before that what makes the difference between a strong student and not a strong student is a student's ability to figure out what to do in a new situation. So if you keep calm and carry on, you'll figure out that, okay, we're talking about kind of mass, maybe the derivative of mass, but there's mass involved, there's force involved, there's velocity involved. Maybe we should just start with impulse. So if we start with impulse, something like that, we say, okay, well, how much force is involved? Okay, so if they want force, maybe we should just, for instance, right, if they're looking for force, maybe we just rearrange for force. Okay, so that's what that tells me. Okay, delta P by delta T. Well, am I told anything about momentum? Not really, but I'm given V and the change in M. Okay, well, I'll realize in the back of my head that momentum is mass times velocity. So this is going to be the change in mass times velocity over the change in time. Okay, so does velocity change? Well, velocity seems to be constant at 20 meters per second. So it looks like I can probably just take velocity out of the delta. Oh, and look at that. What's left is the change in mass over the change in time, which is exactly dm by dt. So that tells you that the average force on your car is going to be 1.5 times v, which is 1.5 times 20, which equals 30 newtons. So there you go. So if you're washing your car with a hose, there's about 30 newtons of force on your car window or door. Okay. So that's sort of an intro to momentum. Just like we did with energy, we talked about work first and some examples with work. And then at the end of the energy unit, we topped it off with the law of conservation of energy, which is a really hefty head honcho law in physics. Well, now we're about to move into another very big head honcho law in physics. In fact, the conservation of momentum honestly probably governs like 99% of what we experience in a day-to-day life. We've already seen how momentum can be used to describe forces with the derivative of momentum with respect to time. And so we already know momentum kind of governs dynamics, and momentum kind of explains kind of everything else we see and experience in everyday life as well. So I would say the conservation of momentum is a very, very, very important concept. Dare I say even more important than conservation of energy, which is saying a lot because conservation of energy is also quite important. It is a very fundamental law. On a related note, in chemistry class, let's take first year chemistry. I honestly, I don't know why I pick on chemistry so much. I actually absolutely adore Judith Poey. She was actually one of my favorite profs in all of undergrad at UTM. I did not enter university liking chemistry at all, and I was not looking forward to taking first year chem at all. I didn't even know who Judith was. And I left that class absolutely in love with chemistry because of Judith. So this is by no means a reflection of Judith. I absolutely adore her. But if you look at chemistry as a whole, first year chemistry, they really only have one law to themselves. And that law can also be broken. So it's not really a law. I mean, the law that chemists really have in first year is, it's actually a principle. It's like the Aufbau principle and the Pauli exclusion principle in quantum mechanics. And you can violate those. In fact, when you violate those, some fun stuff happens. And everything else in chemistry that they call a law is actually physics, like, conservation of mass when you do stoichiometry, and conservation of energy when you do thermodynamics and Gibbs free energy and enthalpy and stuff like that. That's all conservation of energy, which is physics. And in physics class, look how many laws we've done. We've done conservation of energy, conservation of momentum, the laws of motion, Newton's laws of motion. Like physics has all the laws. So like this is why physics is so hard, because like all the fundamental laws of nature that we see around us and that are used in all the other branches of science, they all come from physics. So you're taking a class that really explains everything that is going on around you, and that's probably why it kind of seems so hard at times. Anyway, enough of a side rant. What is the law of conservation of momentum? Just like energy, the law of conservation of momentum says that the total amount of momentum before an event has to be the same amount of momentum after an event. And honestly, this really is kind of the same idea right down to it as the law of conservation of energy. It's just now this is a vector instead of a scalar. So, without further ado, there's really nothing more to say about it other than to just do some practice. But the concept is that momentum is conserved. 100% momentum is conserved. So with that in mind, now knowing that momentum is conserved, that means if you have, let's say you've got two particles in your system, that means the momentum of object 1 plus the momentum of object 2 has to equal the momentum of object 1 after some sort of event. The event could be a collision of sorts, plus the momentum of object 2 after, let's say, a collision. So that's what the law of conservation of momentum says. Mathematically, there is not much more to it than that. So we will go through some examples, but before we do some hardcore examples, I think I've been talking enough right now. My voice needs a bit of a break. Let's do some poll questions. So as per usual, I'm going to make this smaller so you can see it while I have the poll up. So let me start a poll. Oh, there we go, poll. Okay, so I'm going to start the poll now. There we go. I'll read the question. A system of particles is known to have a total momentum of 0. Does it necessarily follow that the total kinetic energy of the system is also 0? One person's cheeky and voted D. Of course. So we know the net momentum is 0. Does that necessarily follow that the total kinetic energy is 0? Okay, there's 60 of you who have voted, 61. So some of you, I don't know, maybe you're still thinking, maybe you stepped out to get a glass of water, in which case you're not going to hear me say this. 62. Okay, for the sake of time, I think I'm going to end the poll and display the results. So I would say, there you go. Most of you got the nail right on the head. The answer is definitely no. There, you can see it there. The reason being is momentum is a vector. So consider this. Well, let me stop sharing the results so you can get your screen back. So consider this. Consider a particle traveling this way with momentum P1, and consider a second particle traveling this way with momentum P2. But the magnitude of P1 equals the magnitude of P2. Well, this means if you vectorially add momentum 1 plus momentum 2, you're going to get 0. They're equal and opposite vectors. So when you add vectorially those two quantities, they're going to sum vectorially to 0. So this satisfies the question, you know, the sum of all the momentums is 0, yes. But does it necessarily follow that the kinetic energies of the system sum to 0? However, this means it's going to have speed. Let's say they both have object of mass m. So let's say they're both going to have speed v. Then the kinetic energies are also going to equal each other. But kinetic energy is not a scalar. So the total kinetic energy is actually the sum of both the kinetic energies. And that's not 0. So that's a very easy example to sort of see how momentum can be 0, but things are still moving, or the system is still moving, but the overall, the center of mass of the system is not moving. And this seems like an easy question, which hopefully it was for a lot of you, but it has some very interesting implications. This means that the center of mass of this system is somewhere about here. And even though this object continues to move this way and this object continues to move this way, the center of mass, which we'll talk about later and maybe tomorrow, stays the same. And this is actually the very notion of our universe. In fact, conservation of momentum is such a prolific fundamental law of physics that it actually governs you know, what we experience in astronomy. You know, there was, you know, the Big Bang happened eons ago. You know, so it all started from a center, you know, that was the center, quote unquote, the center of the universe. The Big Bang happened, and then, you know, all this mass got expelled radially outward. So, you know, we've got, you know, all these rocks that fly, you know, radially outward, kind of everywhere, kind of like this. And our whole universe was kind of born that way, and all of our solar systems, our stars, our planets, our everything was kind of born that way. but it kind of exploded radially outward. So if you, you know, before the Big Bang happened, before the universe existed, the total momentum, obviously, of everything was zero, because nothing existed, nothing was moving. You know, obviously there was no momentum. So after the Big Bang theory, there also has to be zero momentum. So if you actually add up the momentum of everything in the universe, it also has to equal zero. And this is the premise of what astronomy is. You know, if you do study astronomy or astrophysics, or even cosmology, quite frankly, what you're doing is like, we know, yes, the Earth revolves around the sun, but like our solar system itself is actually moving forward. And a different solar system, like the Andromeda galaxy, is moving perhaps at a different speed, perhaps in a different direction. And you know, you can measure the speed of the other galaxy relative to our galaxy, or relative to Earth. And you can kind of figure out, with that, you can kind of map out all the velocities of the things around you, and you can kind of get a sense of where we are in the bigger picture of things. We meaning our solar system, in the bigger picture of things. So that's how, you know, astronomers have kind of figured out where, you know, that we're accelerating away from the center. And if you kind of trace back our trajectory backwards, you can kind of integrate backwards to find where the center of the universe is. And it all boils down to this notion that momentum is conserved. So that's kind of a really interesting, I know it was an easy polling question to do with you guys, but the answers of this easy polling question have some pretty profound implications in our life. Okay, another one. Let me bring up the poll again. Oh, wow, this computer is really slow. Okay, relaunch, continue. Okay, so there you go. The question says, two objects are known to have the same momentum. Do these two objects necessarily have the same kinetic energy? Yes, A, B, no. So 13 of you, 14 of you have responded. If two objects are known to have the same momentum, does that mean they have the same kinetic energies? You can actually kind of use logic to figure out an answer to this. You don't actually need to know physics to answer this question. Okay, we've got 54 of you, 55 of you. If you need to, think of the equations. You know, momentum is mv, and you know kinetic energy is 1/2 mv squared. The two of them certainly have the same variables, for sure, both m and v, right? Okay, we have about 61 of you, which is roughly the same number as we had last time in the last poll. So I'm going to end the poll now and share the results. So 77% of you said no, just because two objects have the same momentum, it does not mean that they have the same kinetic energies. That is true, and about 23% of you, so about a quarter of you, think that it did mean that. So let's stop sharing the results. You can get your screen back. Let's take this up very quickly. Okay, so we know momentum is mv, and we know kinetic energy is 1/2 mv squared. So let's just take some values, for instance. If you take m to be 1 and v to be 2, then this means we'll say m1 and v1, and let's say m2 to be 2 and v2 to be 1. Okay, well, this momentum 1 would be 2, and momentum 2 would also be 2. Okay, so these two objects would have the same momentum in this case. Do they have the same kinetic energies? Well, if you look, EK1 would be 1/2 1 times 4, which equals 2 joules. and EK2 would equal 1/2 2 times 1. And that equals 1 joule. So even though the two objects have the same momentums, they have different kinetic energies. And I give you a hint that you don't actually need to know physics to figure out the answer to this. You can use some psychology and logic. If the two were kind of equivalent, if two objects having the same momentum implied they had the same kinetic energy, then that would kind of render the need for momentum useless, right? If all the information you can obtain from momentum you could also obtain from kinetic energy, then why have momentum, right? So that alone should have sort of indicated to you that no, there's something different between momentum and kinetic energy. And the answer is not the fact that there's a half there. The answer is that V is squared in one of them and not squared in the other one. So the relationship between the Y values, like the dependent value, is different between momentum and kinetic energy. So their behavior is different. They represent different quantities. So the answer is obviously no to that. Obvious after I took it up, of course, not necessarily obvious beforehand. Okay, temporary break in multiple choice questions. So interestingly enough, I've told you that Newton published his second law, F net equals ma, not as F net equals ma, but rather as the derivative of momentum. We can actually represent Newton's third law, which is every force has an equal and opposite reaction force. We can actually derive that using the conservation of momentum. So for instance, we're told that force 1 has an equal and opposite reaction force, right? So minus F1 equals F2, for instance, okay? Well, if we say, we got two objects, we'll say momentum total equals momentum total prime. And I don't know, this tablet seems to be processing something in the background. It seems to be lagging a little bit as I write. So let's assume this is a system of two objects. Then my momentum beforehand is going to be m1 v1 plus m2 v2, and I suppose there are vector signs on those. And this is going to equal m1 v1 prime plus m2 v2 prime. And that's just standard. We did this with energy as well, right? We just kind of wrote out all the terms. We're doing the same thing here with momentum. We just kind of read out all the terms. And we want to show that Newton's third law is actually a law. And if it falls out of the law of conservation of momentum, then any conclusion from the law of conservation of momentum will inherently also be a law. So this says F1 equals, well, minus F1 equals minus F2. That tells me we have to gather everything with a subscript of 1 on one side and push everything else with a subscript of 2 on the other side. So let's do that. M1 V1 vector minus M1 V1, come on, prime equals M2 V2 prime minus M2 V2, vector. All right, there you go. Now everything with the subscript of 1 is on the left, everything with the subscript of 2 is on the right. We can go ahead and factor out an M1 from the left. So we're going to get V1 minus V1 prime. And we can factor out, let's say we can factor out a negative M2 on the right-hand side. So minus M2, and this is going to be oh, actually, you know what? Let's factor out a negative M1 on the left. That makes more sense. So this would be V1 prime minus V1. There we go. V2 prime minus V2. All right. And this is simply minus M1 delta V1 equals M2 delta V2. And we're almost there. now all we do is what we do to one side, we do to the other side. So let's divide the left side by delta t. Let's divide the right side by delta t. And after we do that, we get minus m1 a1 equals m2 a2, which is minus f1 equals f2. So we've actually used the conservation of momentum to show whatever force one object exerts on another object is going to be equal and opposite from the second object on the first object, right? So if you as object one push object two with a certain force F, then object two will push back with the same force that you gave object two. That's what the law of conservation of momentum says. So that's actually where Newton got his three laws from. It wasn't that he just kind of invented them out of thin air. They actually came from momentum, which is kind of interesting. Moving on, just to save some time, I don't think I'm going to launch a poll. We can just talk about this. And by we, I mean I will talk and I'll give you a second to think and then I'll continue talking. A net force of 200 newtons acts on a 100 kilogram boulder, and a force of the same magnitude acts on a very light pebble. How does the rate of change of the boulder's momentum compare to the rate of change of the, oh, I meant pebble. Pebble. This is how you know I type my own lecture notes, when there's typos in them. As you found out from the midterm, typos happen, especially with me. So we are looking for, how does the rate of change of the boulder's momentum compare? So they're looking for the rate of change of momentum. This is the rate of change of momentum, right? The derivative of momentum. Well, the rate of change of momentum, dp by dt, is actually F net. We know this from Newton's second law. It's the net force. So the rate of change of momentum is the net force on the object. So then really what this question is asking is the same net force acting on the pebble as is acting on the boulder? And the answer is yes. A net force of 200 newtons is acting on the boulder, and a net force of 200 newtons is also acting on the pebble, which means they're going to have equal rates of change of momentum. There you go. We have a few more of these to do before we move on. So if you're getting bored of these, I apologize, but they are really good concept questions to really flesh out kind of the new idea. Like I said, there's not a lot of math that's new here. It's just a new idea. You got to get your brain used to the new idea. Will their accelerations be the same? How does the boulder's acceleration compare to that of the pebble's acceleration? I guess there should be an apostrophe there. Again, typo, that's me. That's a grammar typo, which I am definitely me, not an English major. So now that I'm asking for the rate of change of the momentums, now they're asking about the acceleration. So I asked myself, okay, well, what equation do I know that relates force applied and the acceleration? And that is simply F net equals ma. So I say, all right, the question wants to know about the acceleration, right? So that's going to be the net force divided by the mass. So, all right, it's the same net force in both cases. It was 200 newtons. So the acceleration felt by the object is going to be 200 divided by the mass. So the bigger the denominator, the smaller the fraction, or the smaller the acceleration. And the smaller the denominator, the larger the fraction. So whichever one has the smaller mass is going to feel the larger acceleration. So the pebble has a much smaller mass. So the pebble is going to feel a much larger acceleration. So the answer here is, how does the boulder's accelerate? The boulder is going to have an acceleration less than that of the pebble. There you go, less than. And don't let the physics confuse you. Don't get bogged down in all the details. think about this logically. Like physics is like literally physical. Like that's where the name physics comes from. You can touch it, you can feel it. Just think about it. You push a car with 200 newtons of force, it's not really going to go anywhere. So its acceleration is going to be quite small. But if I push, I don't know, if I push an office chair with 200 newtons of force, it's going to move fast, right? So, you know, don't get bogged down in all the equations. Like at the end of the day, if you're confused, think about what'll happen in real life. That's the beautiful part of studying physics, is it's rooted in reality. Okay. Another one. A small car and a large truck collide head on. So maybe you're driving a smart car, I don't know, and you have a head-on collision with a U-Haul truck. Let's hope you don't, but I'm just saying, hypothetically in the question. Which one has the larger change in momentum? Well, conservation of momentum. Momentum has to be conserved. So which one has the larger change in momentum? It has to be the same. Conservation of momentum. If one object has a decrease in momentum because it hit a post and now it stops, whatever momentum lost by one object has to be gained by the other object, right? If you have to be, change in momentum has to be the same. So this just falls out of momentum in the system is conserved. Okay, so law of conservation of momentum. There was a similar question asked in the dynamics section with forces, is when, you know, a small car hits a large truck, which one exerts a larger force on the other one? And a lot of people might think, not necessarily students, but a lot of people would think, oh, a bigger truck would exert a heavier or a larger force on the small car. The small car has a smaller mass, it has less ability to push back. But I can see why you would say that. Really what they're saying intuitively is that because the car has a lower mass, the acceleration it feels during the collision will be different. That's true. But Newton's third law says every force has an equal and opposite reaction force. So whatever force the heavy truck pushes on the light car is going to be pushing with the same amount of heavy force back. But their accelerations will be different. And now you can actually think of this exact idea in terms of momentum as well. One last one, I swear. You were driving around a curve in a narrow one-way street at 80 kilometers per hour. This sounds a lot like me. I would highly recommend you do not drive around a narrow curve on a one-way street at 80 kilometers per hour. We actually did a question earlier where the car was traveling at around 88 kilometers per hour and had to stop in 1.5 seconds, and it was not able to, right? It would overcome static friction and slide. So this is dangerous, I guess is what I'm getting at. It's a very dangerous setup. An identical car, which is statistically unlikely, but hey, why not? An identical car is heading straight towards you on this one-way street. So either I'm driving the wrong way or this other car is driving the wrong way. Someone's driving the wrong way. It's also heading toward me at 80 kilometers per hour. I have two options. I can either hit the car head on, or I can swerve and run my car into a massive concrete wall, also head on. The word massive here really means like it's so large that it's not going to be like, it's not like I hit a tree and I'll just break through the tree and my car will keep going. Like it's a massive concrete wall, I'll hit the wall and my car will stop. What should you do? Meaning, what is more advantageous for me? I don't care about the other guy. What's more advantageous for me? Is it better for me to hit the car head on, or is it better for me to hit the concrete wall? And you have to ask yourself, well, in both cases, what happens to me? Well, if I hit the car head on, it's the same car with the same speed, the same mass. So if you have an object of mass m and an object of mass m traveling at speed v, toward one another, that when they collide, they will both end up stopping, right? They'll just collide together and stop. Same mass, same speed, they'll just collide together and stop. So that's case one. Case two, I'm traveling and I collide with speed v into a brick wall. And final, like after I collide into the brick wall, my final velocity is also 0. So my change in momentum up here is mv. Technically, I should say it's negative mv, right? Because it's 0 minus momentum 1. Momentum 2 minus momentum 1. Momentum 2 is 0. Momentum 1 is mv. So it's 0 minus mv. And then here, my change in momentum is also going to be minus mv. So in both cases, my change in momentum is just mv, which means it actually doesn't matter at all what you do. So here, the answer is C. It makes no difference. In either case, it's the same change in momentum. Makes no difference. Okay. So I'm tired of concept questions now. We have a bit of time left. Let's move on to some actual like textbook-esque problems, so that way you can kind of see how to approach these problems. And then by the end of today's lecture, in another, let's say 20-ish minutes, you will have the ability to open your textbook and do some momentum practice, at least 1 hour, right? That's what I say we as if it was a contract. I'm advising at least an hour. Whether or not you follow that advice is your own prerogative. So before we do jump into an example, let me just say, it's a new chapter, it's a new concept. So what's our method of attack in terms of approaching these problems? And let me be really clear right up front. The answer, really nothing. It's honestly pretty much the same as dynamics. Instead of drawing a free body diagram where you label the forces, you're drawing a momentum body diagram, which is not an actual thing. Do not Google the term momentum body diagram, but you're pretty much drawing a dot, and you're drawing all the momentum vectors of the objects. Now, it's literally impossible to have more than one momentum vector for one object, right? The object itself only has one momentum. So you draw the momentum, that one momentum vector of that one object, in the same way you would draw the free body diagram on forces on an object. And then instead of doing F net equals ma, you write down P total equals P total prime. So it's really the same sort of thing, just with different symbols. Instead of free body diagram F net equals ma, you're drawing a momentum diagram with P total equals P total prime. It's really the same thing. So let me show you what that means. Here's an example. A loaded railway car of mass 600 kilograms is rolling to the right at 2 meters per second when it collides and couples with an empty freight car of 3,000 kilograms rolling to the left at on the same track at 3 meters per second. What is the speed and direction of the pair after the collision? I write the I there for no reason, because as I shrink it, the I is not going to follow. Okay, so a lot of words there. The first read through was kind of wordy and my brain got lost. So I'm just going to read through it again and write down some values. So a loaded railway car of mass, okay, so M1 equals 6,000 kilograms, is rolling to the right at, what is that, 2 meters per second to the right. And it collides and couples with an empty freight car of mass 3,000 kilograms rolling to the left at 3 meters per second. What is the, oh, and they couple together. Okay, and what is the speed after the collision? Okay, so I've written down all my information. It looks pretty clear here, looking at the variables that were given and the variable that we're asked for. It's pretty clear to me that this is a momentum question. Now, obviously, because we're in the momentum lecture, it's obviously a momentum question, but you know, if this was on the midterm, you're trying to figure out, is it energy, is it momentum, is it torque, which we haven't done yet. We'll do it next. Anyway, to me, we're given velocities and masses. So that screams momentum. They're also talking about a collision. And anytime there's a collision involved, that's a pretty telltale sign you have to use momentum. So, like I said, hello? Okay, that was, okay. If we start with a diagram, we have object 1 and object 2. And let's say here we have V1 this way and V2 this way. So there we go. There's the equivalent to the free body diagram. It's not exactly a free body diagram, of course, because they're not forces, they're momentums. But anyway, it's a diagram nonetheless that depicts kind of what's happening. And from here, we do P total equals P total prime. And here we're going to get, what is my momentum before the collision? So before is going to be the momentum of cart 1 plus the momentum of cart 2 equals the momentum of cart 1 after the collision plus the momentum of cart 2 after the collision. All right, so this is a vector equation. Vector equation. So let's assign, let's say right equals positive. Okay, so if right is positive, I ask myself, momentum 1, P1, if you look at your diagram up here, momentum 1 is pointing to the right. So when I drop the momentum sign, it's going to be positive. And when I look at P2, P2 is pointing to the left and right is positive. So when I drop the vector sign, I'm going to put a negative in front of P2. And moreover, with momentum 1 prime and momentum 2 prime, we're told that they couple together. So the two masses will come, you know, trains have the ability to sort of click into one another. So when they collide, they latch and they become one mass, they stick together. So I don't know what the direction is going to be. I don't know if it's going to be left or right. So when we drop the vector signs, let's just assume it's positive. We'll assume it's traveling to the right. And if we're wrong, then that means when we solve, the answer is going to come out negative, which means we know it's going to be negative right, which means left. So let's just assume it's in the right direction for now. So this is going to be momentum 1 plus momentum 2. And we expand the definition of momentum a little bit. So that's going to be M1V1, oh, there's a minus sign there, minus M2V2 equals M1V prime, or V1 prime, plus M2V2 prime. However, we know that they couple together, which means V2 prime equals V1 prime. Whatever the velocity of these objects are after the collision, they're the same, right? The two masses are entwined. They are coupled together, which means whatever the speed of object 1 is after the collision is going to be exactly the same as the speed of object 2 after the collision. So I can actually just combine these and say mass 1 plus mass 2 times, times V prime. Okay, I'm kind of losing track of what they're asking for. Let's just go back and see. What is their speed and direction after the pair collide? So they want to know the speed after. Okay, so let's solve for V prime. That's the speed after the collision. So that's going to be M1V1 minus M2V2 over M1 plus M2. And there you go. That's your equation. And if we wanted to, we could actually go through and punch in all the numbers if we really wanted to. I think if we did that, we would end up getting, let's see here. I think we would end up getting 0.33 to the right So if you did that, it would be a positive value, which means according to our coordinate system, we assumed, or we set right equal positive. So when you did this, you got a positive number in your calculator, which means it was traveling right. Oh, and I forgot to write the units here. That was my apologies. I should say meters per second there. Okay, so that's one example of how you would use the conservation of momentum in a problem. Fairly straightforward. We have some time left, so let's keep going. So I don't know if you've experienced this. There's a notion of recoil. I don't. For those of you who have experience with a gun, hopefully very few of you have intimate knowledge of a gun. But maybe you see it on TV all the time. If you take a gun and you fire it, even if you hold the gun horizontally and you fire the gun, after the bullet sort of exits the chamber, the gun sort of flares backwards. It recoils. And your brain instinctively knows that this is going to happen. This does not confuse your brain. Maybe your conscious brain doesn't know how to quantify it, but your unconscious brain knows that it would happen, that it's a natural thing to occur. So your unconscious brain is actually very savvy when it comes to conservation of momentum. Your conscious brain, however, is perhaps at a loss because you've never really consciously thought about the conservation of momentum before. Anyway, you can explain this recoil behavior using the conservation of momentum. So hopefully after this example, you can become more aware of things exhibiting recoil that you see on TV. Also, I can't even watch TV properly anymore. I'm such a physicist. You watch TV and these action shows and you're like, in real life, that wouldn't happen. In real life, conservation of momentum would mean that guy's dead. And here he jumped off a building and just walked away. It's like, no. Anyway, physics has ruined TV for me. Anyway. So here's a question about recoil. Calculate the recoil velocity of an unconstrained rifle. Unconstrained meaning it's not strapped to the table. No one's holding it down. There's a rifle that's just kind of like sitting on a table and someone kind of pulls the trigger with a piece of string. So like the rifle is free to do whatever it wants, which is very dangerous, but anyway. Calculate the recoil velocity of an unconstrained rifle with mass. Okay, so mass 1 equals 5 kilograms after it shoots a bullet of mass 50 grams. Okay, at a speed of 300 meters per second. At the last known bison. If you play Cards Against Humanity, that would be funny. Okay, so I've written all the variables that we need here. The only tricky thing is realizing that the speed they give you, 300, is actually prime. It's actually after. It's the V2, the speed of the bullet, after the event happened. The event meaning firing the bullet. So we use conservation of momentum again to approach this. So if you want to, we can draw, actually, let me start with a diagram. I'm breaking my own rules here. So let's start with a diagram. That's before, or I should say before. All right, and nothing's moving. The bullet is in the gun is stationary, the bullet is stationary. There's nothing to draw, there's no momentum vectors to draw. And then after, well, this is big, the bullet is small. We know the bullet is traveling quite fast, 300 meters per second, quite fast in one direction. Let's say it's toward the right, but conservation of momentum has to be a thing. So before, you see that there was no arrows, right? The total momentum beforehand was 0. So it doesn't make sense for the after picture to only have one arrow, because that would mean momentum isn't conserved, right? That would mean that there has to be a backwards arrow. And this would balance out, just like forces, right? An F net of 0 means there's a balance in forces. If the total momentum before was 0, then the total momentum after has to be 0. That's kind of the power of conservation of momentum. So I've drawn my diagram like I have advised. We move on to conservation of momentum. So P total equals P total prime. Let's say mass 1 V1 plus mass 2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, so same start as before, exact picture and then conservation of momentum, same setup. And I asked myself, okay, beforehand, no speed of the gun, no speed of the bullet, so my total momentum before is 0. After, let's assume right equals positive again, because these are vectors. We do need a bit of a coordinate system here. So let's assume right is positive. Well, in my picture, the bullet is traveling right. So the rifle is going to be traveling backwards, M1 V1 prime, and the bullet is traveling to the right, so it's going to be positive, M2 V2 prime. Notice here how I'm not writing vector signs anymore. Right, the vector sign above the V1 prime is now no longer there, and the vector sign above V2 prime is now no longer there. So this is what happens when you assign a coordinate system, and that should be a kind of a review of what we did before with kinematics and dynamics and things. And you see here that we're going to get M1 V1 prime equals M2 V2 prime. This pretty much means if there was no momentum before, then the two pieces, the two objects, after the collision have to have the same momentums as each other, obviously. Now, what are they asking for? What is the recoil velocity of the gun? So I guess what they were asking for was V1 prime. So V1 prime is going to equal M2 divided by M1 times V2 prime. And if you plug in all your values, you're going to get something along the lines of 3 meters per second. Backwards. Or to the left, I should say. We know it's to the left. We know it's to the left because we drew it in our picture that way. So ahead of time, we knew it was to the left. So 3 meters per second, I mean, I know that's not as fast as a bullet, don't get me wrong. But I mean, if you're firing a gun in your hand and you pull the trigger and the bullet flies out, picture how fast 3 meters per second is. I mean, can you walk 3 meters per second? Like I know I can't. Like 1 Mississippi. In that amount of time, 1 Mississippi. You have to move forwards 3 meters. Like that's fast to walk. Picture holding a gun up near your face, because that's where guns are held usually, up near your face. And when you pull the trigger, it flies backwards towards your face at 3 meters per second. That's fast. And quite frankly, if it hits your chin or hits your face, it's hitting your face and hitting your body with exactly the same momentum that bullet has, right? Because conservation of momentum, whatever momentum that rifle has to recoil with, is exactly how much momentum it gave the bullet to go forward. So obviously it's not as dangerous as a bullet because a bullet is pointed and very small, so it'll go right through you. But still, it's going to hurt. If that 3 meter per second gun hits you in the face, it's going to hurt. Anyway, that's an example of recoil. I think we've got time maybe for one more question. We'll see. So example, things can bounce off of each other as well. So this is another example of a sort of a collision that happens of a before and an after and a need for conservation of momentum. So a 1 kilogram ball, I'll just read it first. A 1 kilogram ball moving with a velocity of 2 meters per second to the right collides straight on with a stationary ball right after the collision. The 2 kilogram ball moves off to the right with a velocity of this. What is the velocity of the 1 kilogram ball after the collision? Okay, so again, a lot of words. Oop, right click somehow. A lot of words. I'm going to read through it again and just write down the numbers. So a 1 kilogram ball is moving with a okay, so mass 1. Oh, I'm writing in red. Black. Okay. Mass 1 equals 1 kilogram. with a velocity of 2 meters per second to the right. Collides straight on with a stationary ball. So M2 equals 2 kilograms, V2 equals 0. After the collision, the 2 kilogram ball, which is M2, moves off to the right with velocity 1.2. So V2 prime equals 1.2 to the right. What is the velocity of the other ball? And here's the question. We don't even know if the other ball is going to be traveling to the left or to the right. You know, initially it was traveling to the right and it hits a stationary ball, so it's traveling to the right and then hits the stationary ball. The stationary ball is obviously, the force on the stationary ball is obviously to the right, so it's going to move off to the right. But where does this ball go? Does this ball continue through, or does it get, you know, ricocheted backwards? And, you know, thinking of it ahead of time might be challenging, but that's why we use momentum. You can actually just calculate it and just see what the answer is. So start with the picture. So we have a small mass, 1 kilogram, is moving at speed v, and it strikes a stationary larger mass. And then after the collision, the larger mass is moving this way with V2 prime, and then we don't know what's happening to this mass. So there's my kind of diagram. I start with P total equals P total prime. So my total momentum beforehand is just the momentum of object 1, because object 2 isn't moving. Oops. Object 2 isn't moving. And my total momentum after is going to be the momentum of object 1 prime plus the momentum of object 2 prime. Now here I've assumed right equals positive. So that's why this was positive, and that's why momentum 2 prime was positive. Now I don't know where momentum 1 prime is, right? That's the whole question. Is it pointed left? Is it pointed right? I don't know. So I'm going to leave it as positive. I'm going to assume it's traveling right. If I'm wrong, if my assumption is wrong, then when I solve for momentum 1 prime, then it's going to be negative, which means it's the opposite of what I assumed. So let's just go ahead and calculate it and see what it is. So momentum 1 beforehand is going to be m1 v1, and this is going to equal m1 v1 prime plus momentum 2 is m2 v2 prime. And what are we solving for? v1 prime is what we're solving for. So this is going to be m1 v1 prime equals m1 v1 minus m2 v2 prime. And this means that v1 prime is in fact equal to m1 v1 minus m2 v2 prime over m1. And there you go. Now, if you plug in all your numbers, you plug in M1 to be 1 kilogram, V1 to be what, 2. So this is going to be 2 minus M2 is what, 2? Yeah, 2. V1 is 1.2, so it's going to be what, 2.4 all over M1. M1 is 1. Well, that's easy enough. So here you see that 2 minus 2.4 is minus 0.4 meters per second. So the fact that it's a minus means, well, I assumed it was traveling to the right, which is why I left it as positive in the equation. The fact that we got a negative sign means my assumption was wrong, which means I have to say, therefore, M1 is traveling to the right, to the left at 0.4 meters per second after the collision. Okay. Okay, that's all we have time for today. I would encourage you to do some textbook problems after this lecture. If you have time immediately after the lecture, that's of course what I would encourage you to do. If your time zone does not permit that, then maybe go to bed and do some tomorrow. But the sooner you do some practice after this lecture, the better for you because it's all fresh. After you've done some practice problems in your textbook, I encourage you to come back to these lecture slides. I've posted the PDF version of the PowerPoint slides, so you don't necessarily need, you know, this OneNote file that I have. Like these are published online for you. Once you've done some textbook problems, go back and please try this question on your own at home. It's very interesting, actually. I think the solution is perhaps, maybe not. Maybe it's in the type notes. Let me just check the type notes before I let you go. Yeah, the solution is in the typed notes for you. So if you want to check your work, the solution's in the posted typed notes as well. But I don't think we're gonna have time to get to this in tomorrow's lecture, but it's a really interesting question. And it kind of shows you kind of why engines are designed the way they're designed. It kind of explains why gasoline is burned a little bit at a time, and it's why we don't put a grenade on the back of the car and explode the grenade to accelerate the car. So it uses physics to kind of explain why things are burned gradually to get acceleration and not burned all at once. So it's very counterintuitive. You'd think the answer would be the same and it wouldn't matter, but in fact it does matter. And what I'm saying right now is out of context because you haven't read the question yet, but hopefully after you've done some homework and you come back to this, you can come back to the video and listen to what I had to say again. And hopefully after you read the question, you know, that little summary would make more sense to you. Okay, so tomorrow we've only been doing one-dimensional momentum. So just like we did with dynamics, tomorrow we're going to do two-dimensional momentum, moving from one into two dimensions. And spoiler alert, it's really no different than what we did with F net equals ma. We do F net x equals max, F net y equals may. Here we're going to do momentum total x equals momentum total x prime, momentum total y equals momentum total y prime. Right? You just do conservation of momentum twice. So surprise. Anyway, thanks for watching, and I'm going to stop the recording now. And if you're watching on YouTube, I will see you tomorrow. For those of you who are still with me, I will open the chat momentarily. Ciao for now.